Every second, billions of computers process enormous amounts of information. Yet some problems remain beyond the reach of today's fastest machines.
Some scientific problems are so complex that even the fastest supercomputers could take thousands, or even millions of years to solve.
The electron behavior is highly unstable.
It's deviating from the standard model significantly.
Classical computers store information as bits, using only 0 or 1. Quantum computers use qubits, which follow the laws of quantum physics. While a classical bit is binary, the qubit harnesses superposition, existing simultaneously in multiple states until measured. The error rate on the Y register is stabilizing.
Yes, the coherence time is extending as predicted. Qubits exchange pulses of light, visualizing the complex dance of quantum information processing.
Unlike ordinary processors, a quantum chip controls delicate qubits using extremely precise signals. Every interaction must be carefully. Quantum processors do not work alone. Ultra-precise control electronics send microwave signals that manipulate each qubit with extraordinary accuracy.
The thermal anchoring looks stable.
Confirmed. We are ready for the cooldown procedure.
At room temperature, qubits quickly lose their quantum state. Cooling the processor to temperatures close to absolute zero greatly reduces interference.
The external noise levels are peaking right now. No.
Yes, but the qubits remain perfectly stable.
When outside interference affects a qubit, it loses its delicate quantum state. This process is called decoherence and is one of the biggest challenges. Because qubits are extremely fragile, quantum computers use error correction techniques to detect and reduce mistakes. This helps keep quantum calculations accurate for longer periods. Stable qubits and error correction, a quantum processor can execute quantum algorithms. These algorithms solve certain problems using methods that are fundamentally different from classical computing.
Quantum computers are designed to simulate nature itself. By modeling atoms and molecules more accurately, they could help scientists explore new materials.
Notice the hydrogen bonding at this node. It seems unusually stable.
Yes, that confirms our hypothesis about the protein folding.
Finding a new medicine requires testing countless molecular combinations. Quantum computing may help researchers analyze these possibilities more. Scientists use advanced computing to study materials at the atomic level. Quantum computing may help discover stronger alloys, better batteries, and more efficient electronic materials. The predictive models are showing a sharp increase in market volatility over the next quarter. We need to advise our clients to hedge their positions immediately. The team monitors global traffic in real time. When a threat is detected, their response time is critical. Climate models require enormous computing power. Quantum computing may help scientists improve complex simulations, supporting better understanding of weather patterns and Earth's changing climate. Artificial intelligence depends on enormous computing power. Researchers are exploring how quantum computing could work alongside AI. Artificial intelligence requires enormous computing power. Researchers are exploring how quantum computing could work alongside AI to solve certain complex optimization and scientific problems more efficiently.
The simulation shows an optimization here. Yeah.
That should improve the throughput significantly.
All right, team, the telemetry data is streaming in now.
Confirmed. We have visual lock on the target galaxy.
The calibration looks good.
Systems confirm successful alignment. We're ready for the next phase.
This is where a real quantum computer operates. Every experiment takes place inside a carefully controlled environment, where even the heart of a quantum computer is hidden deep inside a dilution refrigerator. This remarkable machine cools the quantum processor to temperature. Every quantum experiment begins with a carefully designed quantum circuit. The instructions are sent to the processor, where the qubits execute the calculation under precise control.
The calibration seems stable. Let's cross-reference this against the theoretical model to be sure.
The fluctuation aligns with the calibration metrics.
I am logging the data now.
Quantum computers are shared through secure cloud platforms. Scientists, universities, and research teams can submit experiments remotely.
Quantum computing is a global scientific effort.
Inside this sterile environment, advanced robotics meticulously fabricate the quantum chips, a process requiring absolute precision.
Inside the clean room, robotic systems meticulously coat a silicon wafer with ultra-thin materials before the lithography process begins.
After inspection, the quantum chip is carefully packaged. Tiny electrical connections link the processor to external control systems, preparing it for installation. After inspection, the quantum chip is carefully packaged. Tiny electrical connections link the processor to external control systems, preparing it for installation.
The pumps are stabilizing now.
Temperatures on stage 2 are dropping fast.
Good, let's monitor the mixing chamber next. The calibration is holding steady. Yeah. I'm increasing the microwave power now, monitoring the coherence time.
Calibration is complete. The quantum processor now performs its first controlled quantum circuit, allowing researchers to verify qubit behavior before larger scientific experiments begin. The error rate on the repeated circuit experiments is fluctuating too much.
I agree. The AI diagnostics show significant variance in the probability charts.
The fidelity metrics are exceeding expectations.
Yes, the coherence time is remarkably stable as well.
One important application of quantum computing is optimization. Researchers are exploring how quantum algorithms may solve certain complex scheduling and
The quantum processor is handling the variables flawlessly.
Look at the optimization on the transatlantic shipping lanes. Drug discovery requires enormous computational power. Researchers are investigating how quantum computing may improve molecular simulations and support the search for future medicines.
The atomic structure shows promising lattice strain right here.
Yes, that correlates with the increased tensile strength we measured earlier.
Toroidal field stability is decreasing.
Adjusting the magnet current now.
The atmospheric coupling seems unstable in the equatorial region.
I agree. Rerunning the simulation with the quantum processor now.
Getting a fluctuation on the trajectory projection here.
Rerouting the simulation now. Confirm stabilization. As quantum computing advances, researchers are developing quantum-safe encryption to protect digital communications. New
scientists are developing quantum networks that could connect future quantum computers. These experimental systems aim to exchange quantum information across secure communication links.
The simulation demonstrates how quantum entanglement allows for instantaneous communication between these qubits, forming the basis of the processor's power.
The optimization algorithm needs refinement here.
I agree. Let's adjust the parameters before the next run.
Requests are spiking in the Asian sector. Acknowledged. Optimizing the qubit allocation now.
Scientists are developing several types of quantum computers. Each technology has unique advantages, and researchers continue exploring which designs.
The qubit fidelity is holding steady above 99%.
Error rates look good too.
Building larger quantum computers requires adding more reliable qubits while keeping them stable and accurate. Scaling quantum hardware remains one of the greatest engineering.
Error rates are significantly lower than the previous prototype.
Yes, the qubit stability is holding steady as we scale up.
As quantum processors grow larger, correcting errors becomes even more important. Advanced error correction is one of the key technologies needed to build.
Instead of relying on a single processor, researchers are exploring ways to connect multiple quantum processors. Scaling quantum systems could enable
Quantum computers are not designed to replace classical computers. Instead, they work alongside them, tackling specific problems where quantum algorithms may offer.
The decoherence rate is stabilizing right at the threshold we predicted.
If we can maintain this for the next cycle, we'll have a breakthrough.
Researchers are exploring how quantum computing may improve manufacturing by optimizing production schedules, reducing waste, and increasing efficiency in complex industrial systems.
The simulation shows promising results with this compound.
Let's cross-reference it with the patient data we just processed.
Analyze the AI data processing visualization on the main screen. The market trends are shifting rapidly.
The predictive model suggests shifting the traffic flow. I'm updating the parameters now to optimize the grid. The battery storage is fluctuating. I'm adjusting the wind turbine output to compensate. That should stabilize the grid.
The turbulence here is higher than expected.
We might need to adjust the angle of attack on the next pass.
The yield projection has increased by 3%.
That confirms the efficiency of the autonomous units.
Understanding Earth's environment requires processing enormous amounts of scientific data. Researchers are exploring how quantum computing may improve environmental. Quantum computing is moving from research toward practical applications. Around the world, scientists continue improving this technology through careful experimentation and innovation. Analyze the AI data processing visualization on the main screen. The market trends are shifting rapidly. Measurements. The next major goal is fault-tolerant quantum computing. Scientists are working to build quantum systems that can perform long, reliable calculations. The future of computing is expected to combine classical and quantum systems. Each machine will perform the tasks it does best. Researchers are developing quantum networks that could securely connect future quantum computers, allowing them to exchange quantum information across long distances. The decoherence time is still too short. We need to adjust the frequency stabilization parameters and run the sequence again.
The error rates are stabilizing now.
Good. The processor has maintained stability for 12 hours.
The dynamic allocation map shows the bottleneck here.
Yeah, we can reroute that segment if the QPU optimization holds.
Let's run the simulation again.
The simulation confirms the error correction protocols are functioning within the tolerance.
Yes, and the entanglement stability metric is holding steady.
All right, the processor is seated.
Confirming connection now. Looking good. Performance metrics are spiking.
The error rate on this simulation is significantly lower than the last run.
Yes, the AI optimization is working perfectly with the quantum processor.
Large-scale quantum systems require constant monitoring and precise control. Every experiment helps scientists improve reliability. The qubit count confirms we are tracking exponentially with the timeline. This breakthrough changes everything for scaling the processor. Quantum computing is still an emerging technology. Scientists continue improving hardware, software, and algorithms to unlock new scientific and industrial possibilities in the years ahead. Quantum hardware is only part of the system. Scientists and software engineers develop quantum programs and algorithms. The classical supercomputer prepares the data here. Then it's transferred to the quantum processor for the heavy lifting.
The calibration seems stable now. Yeah.
Yes, the coherence time is holding steady on the AI diagnostics.
The qubit stability is holding perfectly at 5 nines.
And look, the optimization algorithm is already reducing the error rate. This is a major breakthrough.
Quantum computing has advanced through decades of scientific research and engineering. Each new generation delivers better performance, improved stability, and
the calculations are successful, and the system metrics are stable.
It seems we have achieved quantum supremacy.
The qubit is stable.
Initiating global data synchronization now.
Let's go! We got him! Thanks for the support, guys. Make sure you hit that like and subscribe button right now.